Alright, today we're going to be talking about the Open Shortest Path First version 2 protocol. So the origin of OSPF is that it was created in 1987 by the OSPF working group of the Internet Engineering Task Force. It's had 3 versions and 1 update since. The most recent update was to include IPv6 addressing. OSPF specification is published as Request for Comment RFC number 1247 and is registered with the Network Information Center as IP protocol number 89. OSPF is based on the SPF algorithm, which is sometimes referred to as Dijkstra algorithm. Not sure I said that right, but that's looks good to me. It's named for the person who is credited with its creation. So what is OSPF? Well, it's classified as an interior gateway protocol. Some of the other ones are RIP and IRGP or enhanced IRGP. It's designed for use in TCP/IP internet environments, and it is a link state routing protocol. That's one of the major differences between it and IRGP and eIRGP. Link state protocol is basically a routing technique in which each router shares information with other routers in order to determine the best path within a single autonomous system. A single autonomous system basically is a group of routers exchanging router information via a common routing protocol. So it's also classless, which means it supports variable linked subnet masking and CIDR. That's different than, say, RIP, where it did not take subnet into account. So as far as autonomous systems go, the main feature of OSPF is the ability to create groups and hosts. So similarly to subnetting, each address range is defined in an address mask pair. However, how it's different is that you can actually include many separate networks in this range. So instead of breaking down one network into a smaller range like subnetting, you can do it this way, or you can actually include multiple networks into one range. So the routers inside the same area are going to have identical link state databases, and the backbone, which is default area 0, contains all the area border routers. So between the areas, the backbone routes using 3 pieces: a area called the intra area, which is the source device to the backbone. And then you have the backbone path, so if it has to jump through routers to get to another area, this is the backbone path. And then there's a second intra area, which is basically the remaining path to that destination. Another cool thing about OSPF is you can use virtual links to add control for routes taken in between intra-area traffic. So if you didn't want to go through the backbone, you could actually create a virtual link from one area to another, bypassing the backbone or other routes. So different routers that are going to be used or classified in OSPF are internal routers. So this is just any router that's in the same area as another router. Again, they're all going to have a single copy of the SPF algorithm. Then you have the area border routers, which is a router attached to two or more areas. Then and these will run several algorithms, one for each area they're connected to. So then you have backbone routers, which is a router that has an interface to the backbone area. This may or may not be an area border router. So sometimes you'll have one main backbone router that won't be inside any other area. And then you have the AS boundary routers. May or may not be part of the backbone. It may be an internal or area border router, but it's basically its job is to provide a path to each autonomous system boundary. So just think of it kind of as a default gateway. So speaking about routers, there's in each area you're going to have a designated router, which is elected to serve as the central point for exchanging routing information. There's another router that will be elected as the backup in case something happens to the designated router. And by default, the router with the highest OSPF priority will become DR. They're all set to 1. So you have to actually change the priority number manually if you want to set a specific router to be the designated router. And otherwise, a tie is going to result with the highest router ID to win. So if you have a .1 and a .2, the .2 will win. And each router that is not the DR or BDR will use only the DR or BDR to exchange information. OSPF uses 2 multicast addresses. 224.0.0.6 is send to designated routers and backup designated routers only, and 224.0.0.5 is the address to send to any OSPF router. So each router establishes a full neighbor relationship with the DR and BDR, and the whole point of this is to reduce the number of adjacencies needed, thus reducing the size of the routing table. So if a bunch of students were told to get phone numbers, email addresses, and whatever other information from an entire class, this would basically delegate one student to say, hey, go get everyone's information, put it in an Excel spreadsheet or whatever, and then give a copy to everyone else. And if someone changed phone numbers or any of the other information, basically that person would go and tell this one person, and a new copy would be distributed to everybody else. So makes the work a lot less chaotic, and just kind of increases the reliability of everything. So it also generates, the designated router also generates a link state advertisement on behalf of the network. The link state advertisement includes the set of routers currently attached to the network. So link state advertisements are units of data describing the local state of a router or network. Some of the information include state of interfaces and a list of adjacencies. Again, that's how they flood using the 224.0.0.5. It sends to all OSPF and 224.0.0.6, which will send to only designated routers, and the collective LSAs make up the protocol link state database. So there's 5 types of LSAs. You've got type 1 is the router LSA. It's information describing the state and cost of the router's links to the area. So it's cost is another term for metric that OSPF uses. Then they have the network LSAs, which is type 2, and it is information in which an area contains 2 or more routers, and these are created and sent by the designated router. Then there's types 3 and 4, which are classified as summary LSAs. They're originated by the area border routers to describe inter-area destinations. Type 3 is when the destination is an IP network, and Type 4 is used when the destination is an autonomous system boundary router. Then the last type, Type 5, are autonomous system external LSAs. They're originated by the AS boundary routers, and they describe specific destinations external to the autonomous system. Again, this is kind of using a default gateway. So these are the fields of the protocol packet. They've got a version type, a packet type, the link, the router ID, who's sending it, the area ID, who it's going to, checksum, and then authentication type, so that it knows what procedure to use. So hello packets, they're used to acquire neighbors. Again, it uses multicast 224.0.0.5 to send to any OSPF router. Hello packet fields must be identical between 2 routers to communicate using OSPF. Subnet area ID, hello, and dead interval times, which basically is how many times it will send a hello, how many seconds in between hello requests it will send, and then a dead timer, which how much time until you administratively put that consider that interface or router down since it has not been responding. And then also that the authentication must be the same, and the MTU must be the same. So database description packets, it's type 2 of the types of protocol packets that can be sent. It's basically exchanged when an adjacency is being initialized. It describes the content of the link state database. Sometimes this will take multiple packets to completely describe, and there will be a master-slave relationship. Basically, the master is sending, the slave acknowledges that it received it, and they have a response sequence number to keep track of the information to make sure things aren't happening out of order or packets don't get lost. So they have the link state request packets, which is type 3. It's used to update database information that is out of date based on database description packet exchanges. So only a request is sent from information that is not current, and basically you'll see that the age, the sequence number, and the checksum will let a router know if it has any missing fields from the designated routers tables. Type 4 are link state update packets. This can be sent to one or more LSAs. If only one router needs this information, it'll actually send it unicast. But if it's trying to send to multiple routers, it'll use the multicast address. And acknowledged by link state acknowledgement. When a specific LSA transmission error occurs, LSAs are sent directly to the neighbor that did not return with the acknowledgement of the link state. The link state acknowledgement packet is used to make flooding of LSAs reliable. So multiple packets can be acknowledged in a single LSA packet, and it can be sent unicast or multicast, which again you can send to all OSPF routers or all designated routers. So these are just some examples of the routing tables. It'll just kind of basically based off the LSAs, each router constructs a shortest path tree using the OSPF algorithm with itself as root. So to summarize everything up, OSPF this is OSPF in a nutshell. When a router starts, it first initializes the routing protocol data structures. The router then waits for indication from lower level protocols that its interfaces are functional. A router then uses the OSPF's hello protocol to acquire neighbors. The router sends hello packets to its neighbors and in turn receives their hello packets. The router will attempt to form adjacencies with some of its newly acquired neighbors. Link state databases are synchronized between pairs of adjacent routers. That's the master-slave relationship. Routing updates are sent and received only on adjacencies. So the last part is a router periodically will advertise its state, which is also called the link state. A link state is also advertised when a router's state changes. So if it goes down, if it has an error or anything like that, it will advertise. Router's adjacencies are reflected in the contents of its LSA. This relationship between adjacencies and link state allows the protocol to detect dead routers in a timely fashion. LSAs are then flooded throughout the area. The flooded algorithm is reliable, ensuring that all routers in an area have exactly the same link state database. The database consists of the collection of LSAs originated by each router belonging to the area. From this database, each router calculates the shortest path tree with itself as root, and this shortest path tree in turn yields a routing table for the protocol. Well, that is all I have today for OSPF. I hope it was informative.